Hello, everyone. Welcome back to my class. Here is the day 4 in our ongoing uh, JAMB practice on phases, and we have been on this particular question, which is a 2025 past question. And in our last class, we solved from question 21 down to 30, and today we're going to start from question 31. I hope we are together. So the first question here says, the question says, which of the following statement is true regarding the dispersion of light? So option A says, violet light deviate the most, while red light deviate the least when passing through a prism. B says, the refractive index of a medium is the same for all colors of light. C says, the dispersion is independent of the refractive index of the material. D, the speed of light in a vacuum is different for different colors. So the correct option here is option A. Remember, dispersion of white light is the separation of white light into its component colors, such as that is, we use this Roig beef, that is red, orange, yellow, green, blue, indigo, and violet. So when white light is passed through a glass prism, it refracts. Here's the white light, and separate into its component. So starting from red, the patch of light starts from red, orange, orange, yellow, blue, green, blue, uh, indigo, and violet. So as you can see, the least deviated is red, while the most deviated is violet. So violet deviate most and red deviate least, which is the correct option. I hope this is understood. So that is about question 31. Question 32 says, uh, an ancient wooden artifact is found to have 1/8 the amount of carbon 14 as a fresh sample of wood. The half-life of carbon 14 is 5,730 years. What is the age of the artifact? So this question, we can solve it in these two methods. You can use Zepwa's method, you can use a normal method. Since we have that 1/8 of the amount of carbon as a fresh sample, so we have, and the half-life is what? Is 5,732 years. So we use this breaking down method, that is after first half-life, after first half-life, are we together? Or after a one half-life, what will happen? What is half-life? Half-life is the time taken for half the initial number of atoms to what? To disintegrate. Is that understood? So 1/2 will now be remaining, half will be remaining, right? Will remain after another half-life, after second half-life. Then we have 1/2 of this, that will give us 1/4. That is half of this rather. Half of this, that is give us 1/4 remaining, right? Then after another half-life, after the third half-life, we have half of 1/4, that will give us 1/8 here. So remaining. So since we have gotten at 1/8, which was given to us in the question, so it shows that the number of disintegration, or the number of half-life we have, is what? The number of half-life we have, n, is equals to what? 3. Is that understood? So for us to get the age, or the time of what? Of disintegration, the age of the artifact will be equal to number of half-life multiplied by the uh the half-life. Is that understood? which will give us, this implies that T, or the age, will now be equal to 3 multiplied by the half-life, which is 5,730. So when you press a calculator, you should have 17,190 years as the age of the artifact. Is that understood? Which is option what? Option D. We can use another method known as Zeboas method. In this method, we says I have done a particular video, a comprehensive calculation on this particular method. You can check my video on my channel to watch them and understand. So we have several methods that we can use. One of the methods is that the number of disintegration, right, or number of half-life is equal to time of disintegration all over what? All over half-life. Is that understood? Take note of this one. Then we have that fraction of atom remaining is equal to 1 all over disintegration ratio, which is R. So from what we are given here, this is the fraction of atom of the artifact within remaining, so which is 1 all over 8. So this will give us 1 over 8 equal to 1 over R, which implies that what? That R will be equal to 8. So we have this formula that disintegration ratio R is equal to 2 raised to power what? N. Is that understood? Please watch that my video. A lot of these I've trashed them in that particular video. So our R, disintegration ratio, is 8 equal to 2 raised to power N. So I can also write this in terms of base. I have 2 raised to power 3 will be equal to 2 raised to power N. This implies that N is equal to 3, which is the same thing as what I have here. So we have gotten our N to be equal to 3. You now come back to this formula. N is equal to T all over what? All over half-life. Therefore, the time of disintegration, which is equal to number of what? Disintegration that, multiplied by half-life. That will give us 3 multiplied by the half-life, 5,730, which will give us the same answer, which is 17,190 years. I hope this is understood. As simple as this for the Zeboas method. If you can also use this method, good and fine. It is also straightforward. Is that understood? So that is about question 32. So moving on, so question 33. Question 33 says 2 wires, one of steel and one of copper, are of the same length. They are of the same length, right? Take note of this as we are moving. Of the same length, the length are the same. That is, length of copper is equal to length of the steel. And cross-sectional area, the cross-sectional area is also the same. They are stretched by the same force. So the force applied on the steel is also the same force applied on what? On the copper. If the Young's modulus of the steel is twice that of copper, what is the ratio of the extension of this on the steel wire to the extension of the copper wire? So solution here, since this is objective quickly, remember I've done a particular video on elasticity, what is elastic properties of solid, and the relationship between Young modulus is already trashed there. So please watch the video and get more understanding. We have that Young modulus is equal to stress all over strain, right? So we can write this. Our stress is force all over area, and our strain is extension all over original length. From here, this implies our Young modulus will be equal to FL all over AE, right? Fraction by fraction. So FL over AE. So from this question, the length of what here is steel, here is steel, and here is what? Copper, for instance. So we're going to use S for steel and C for copper. So length of steel, LS, is said to be equal to what? Length of copper, right? And the cross-sectional area of steel is said to be the same as the cross-sectional area of what? Of copper. Also, the force applied on what? On steel is said to be equal to force applied on what? On copper. Is that understood? So, and that the Young modulus on steel is twice of what? Of copper, is 2 times Young modulus of what? Of copper. Is that understood? So we are going to write from this formula we have here, we are going to make, since we are looking for E, we're looking for E, what we are looking for is extension on solid ratio, extension on what? On copper. Is that understood? So since that is what we are looking for, from this formula, we make E subject of the formula. So if we make E subject of the formula, from this formula, right, we have Young modulus is equal to FL all over what? All over AE. Is that understood? So to make E subject of the formula, since we are looking for the ratio of E, so that is our concern, we make E subject of the formula from this relationship. In doing that, you cross multiply, you have Young modulus multiplied by AE is equal to what? Is equal to FL. Is that correct? So that E will now be equal to FL all divided by what? Young modulus times what? Area. Is that understood? So having done this, I'll write for what? Extension for S will be equal to F for S, the force on solid, L for S, length of the solid, all over Young modulus for the solid, and what? Area for the solid. Understood? Then extension for C will be equal to F for C, length for the copper C, all over Young modulus for the copper C, and cross-sectional area of what? Of copper AC. So now that implies that E extension ratio, extension on copper, which is the same thing as ratio is a form of fraction, that is extension on solid all over extension of what? On a copper. So this implies anywhere I see extension in solid, I'll put the whole of this. So that is F solid, force on solid, length of solid, all over what? Young modulus on solid, right? Area on what? On solid. All divided by the extension of copper. I will now put what? F of copper, the force of copper, L on copper, the length of copper, divided by what? The Young modulus on copper, and what? And the cross-sectional area on a copper. So having done this, it's also a division of fraction by fraction, and I believe you know how to tackle it. So this will be force on solid, length on solid, all over Young modulus on solid, and cross-sectional area on solid. This bigger division turned to multiplication. This one become the numerator, and the numerator here become what? Denominator. So I have Young modulus on copper, cross-sectional area on copper, all over the force on copper, then the length on copper. Here now, remember that we were told that the length of solid is same as length of copper. So anywhere I see length of solid, I will replace them by what? By copper. So anywhere I see S, I'll put what? C. So I have FC now, right? LC. So FS solid is same as what? Copper. So anywhere I see copper solid, I'll put what? Copper all over what? For the length, for the length and this, right? For the length, for the force, and for the area. But for the Young modulus, we are told that the Young modulus for solid is 2 times Young modulus of what? Copper. So anywhere I see Young modulus for solid, I'll put Young modulus for 2 times Young modulus of copper. So here I see Young modulus for solid, I'll put what? For steel, I'll put what? 2 Young modulus for copper. Then anywhere I see area for solid, it now becomes area for copper. Then multiply by Young modulus for copper, area of copper, all over F solid force on copper, and what? The length on of copper. So that this can go with this. This one can also cancel this. I'll be left with what? So E on solid ratio E on copper will now be equal to Young modulus on copper all over 2 Young modulus on copper. So that this one will cancel this one. I'll be left with what? 1 all over 2. Therefore, our extension on solid ratio extension on copper will be equal to 1 ratio what? Ratio 2. So that is option what? Option C, 1 ratio 2. I hope this is understood. So that is about question what? 33. Please, if there's anything you don't understand, it is very simple. Just go backward and watch it again. Trust me, you're going to understand it. So that is question 33. So moving on to 34. 34 says the critical temperature of a gas is the temperature A above which it cannot be liquefied regardless of the pressure applied. B, at which the average kinetic energy of the molecule becomes zero. C, at which the gas behaves ideally. D, below which the gas cannot exist in gaseous state. The correct answer is option A. Please, all these things you take note of it so that question can repeat itself. So before we move that, what is a critical temperature of a gas? It is the highest temperature at which the gas cannot be converted into liquid, that is liquefied, right? By pressure alone. The temperature at which the gas cannot be liquefied by pressure alone. So above this temperature, no matter how much pressure you applied, the gas cannot be converted into liquid. So that is why the correct answer here is option A. I hope this is understood. So moving on to question 35. Question 35 says a photoelectric surface has a work function of this electron volt. Light wavelength of 200 nanometer is incidented on the surface. What is the maximum kinetic energy of the emitted photoelectron? Given that Planck constant is this, the speed of light is this, and 1 electron volt is something as 1.6 exponential minus 19 joules. So solution, when the light falls on a metal surface, in the process known as photoelectric effect, there's what is known as work function, which is the minimum amount of energy needed to emit the electron, right? And when this happens, it also, after electron has been emitted, it has to leave the metal surface and it has to have what? A kinetic energy. So that is why the energy of the photon is said to be equal to the work function plus the kinetic energy needed for the emitted electron to leave the metal surface. Is that understood? And the energy of the photon is given to be hf, the Planck constant times the frequency of the emitted electron. Is that understood? Which is equal to work function plus what? Kinetic energy. But in this our parameters here, there's no way we're giving a frequency. So what we are giving is a work function. Our work function is said to be 4 electron volt. We are giving the lambda, the wavelength, to be 200 nanometer, which is something as 200 times 10 raised to power minus 9 meter. Please take note of these conversions. What is the maximum kinetic energy? We are looking for the maximum kinetic energy, which is not known, and Planck's constant is given to be 6.63 times 10 raised to power minus 34 joules second, and we are giving C to be equal to 3 times 10 raised to power 8, right, meter per second. For the in case of conversion, 1 electron volt is said to be 1.6 times 10 raised to power minus what? 19 joules. So from here, we can decide to calculate the energy of the photon before we apply this formula. So the energy of the photon E, as I said, is equal to hf. So since F is not given, but we know that C is equal to what? F lambda, right? So we can write F in terms of C and lambda, which implies F is equal to C all over lambda. Therefore, in this energy formula, energy of the photon, you have H. Anywhere you see F, you put C over lambda, you have Hc all over lambda. So I can now calculate the energy of the photon. H, which is Planck's constant, is given to be 6.63 times 10 raised to power minus 34. Is that clear? Multiplied by the speed of light, which is 3 exponential what? 8, all divided by the lambda, which is 200 times 10 raised to power minus 9 meter. So when you press your calculator for this, you're going to have the upper one, the numerator, to be 9.945, right? 9.9945 times 10 raised to power minus 19, then divided by 200 times 10 raised to power minus 9. So when you divide, that should give us a okay, when you multiply the above, that should give us 1.9 rather, 1.98, 1.98, 1.989, right? That should give us, let me clean this, 1.989 times 10 raised to power minus 25. So divided by this, that is what will give us 9.945 times 10 raised to power minus 19 joules, right? So our energy is in joules, but our work function is electron volt. It's either you convert everything to electron volt or you convert this one to joules and work in a, right? But our option is in electron volt. So we have to convert this energy in joules into electron volt. We know that 1 electron volt, right, is equal to 1.6 times 10 raised to power minus 19 joules. Therefore, 9.945 times 10 raised to power minus 19 joules will now be equal to 9.945, right, times 10 raised to power minus 19, all divided by 1.6 times 10 raised to power minus 19. And that will give us our energy of the photon to be equal to 6.22 electron volt. So since we have gotten this, you come back to this formula, energy is equal to work function plus electron volt, plus the kinetic energy, right? So that our kinetic energy now will now be equal to the energy of the photon minus what? The work function. And that will give us a 6.22 minus work function is 4 minus 4, which will give us a 2.22 electron volt. I hope this is understood. That is option what? Option 2. So if you know what you are doing, all these things is just, we know it's now exam settings. You don't need to do all this. If you know how to apply a formula quickly, you can get your answer. Or for better understanding and for better accuracy, you can just itemize what you have quickly and apply your formulas and get your answer. I hope this is understood. So that is about question 35. Moving to question 36. So question 36 says, Question 36 says an electrochemical equivalence Z of a substance is 0.00112 gram per coulomb. What current will deposit 2.24 gram of the substance in 10 minutes? So this is under Faraday's law of electrolysis, which says that the amount of substance deposited or the mass of substance deposited during electrolysis is directly proportional to the amount of current or the electricity that is passing through the electrolyte. That is, the mass is proportional to the current and to the charge, right? And charge is equal to what? IT. That's understood. So that will have M is proportional to what? IT. When you remove the constant of proportionality, you have M is equal to ZIT. And this constant is known as a electrochemical equivalent. So having known this, we are given that Z is equal to 0.00112 gram per coulomb. And the mass deposited during the electrolysis is 2.24 gram. And the time of deposition is 10 minutes. So make sure you convert to second. That will be 10 multiplied by what? 60, which will give us 600 seconds. So having done this, the next thing you do is to apply your formula. We have M is equal to ZIT. And this time around, we are asked to find T. So I. The amount of current is what we are looking for. So I, making I subject of the formula, divide both sides by ZT. I have M all over ZT. So that will make our M, which is 2.24, all divided by Z, 0.00112, multiplied by T, which is 600. So I will now be equal to 2.24, all divided by, when you multiply the denominator, you have 0.672, and if you divide numerator and denominator, you get 30.30 amp. I hope this is understood. Please, I want you to go along with me. If I ask you to divide, you divide and confirm the answer is correct. If it's not correct, please let me know in the comment section. So that is about question 36. We'll move to question 37. So question 37 says, the electrostatic force between two charges is considered a conservative force because it depends on velocity. B, it causes friction. C, the work done is path independent. And what? And D, it only acts at a distance. But before we move on to the answer, what is conservative forces? Conservative forces are those forces that are path independent. That is to say, uh, it does not depend on only, it does not depend on how things are moved through a particular path, but it depends on the starting and the what and the ending point. For instance, if you are moving a charge from point A to point what? B along the straight line. If you are moving it through a zigzag pathway, right, from point A to point B, or you are moving through a curved pathway from point A to B. So the work done in doing this does not depend on how you move. It depends on the condition of the starting point and the what and the ending point. If the starting point is here and the ending point here are the same with the starting point and end point in the other two parts, then the work done will be the same. So that is why it's path independent. Is that understood? So examples of conservative forces are electrostatic force, gravitational force, and also spring force. They are all examples of a conservative force. So non-conservative force is opposite of conservative force. This one, energy is lost in the course of what? In the course of work done. Example is friction, air resistance, and viscous drag. Are we together? So that is about that. Therefore, our answer for my explanation, I believe you have known the answer, which is option C. The work done is a path independent. Is that clear? That's about question 37. 38 says, why is the speed of sound independent of amplitude? What is amplitude? That is the maximum displacement of body from what? From its equilibrium position. Is that correct? So option A says because sound is a linear wave, uh, um, and B, because amplitude is always constant. No, it's not constant because it depends only on frequency. No, the speed of sound does not depend on the frequency. V or C is equal to F lambda. It depends on the frequency and also the wavelength, right? And because of inverse law, so that is not correct. The only correct answer here is option A. It depends in a linear condition such as air. The speed of sound depend on the properties of the medium, such as the density, right? When it changes, the density is different, then the speed of sound will also what? Also different. Is that understood? So it depends on the density, temperature, and all other uh, properties of what? Of the medium the sound is passing through. Is that understood? That is option A. That is the correct answer. So moving on to question 39. So question 39 says, what happens during electrical breakdown of a gas? Electrical breakdown of a gas simply means ionization of gas, as in the process through which gas what? Conduct electricity. Gas at a normal condition does not conduct electricity unless it is taken through a critical condition, which is what? the condition at which it conducts electricity about approximately a very low pressure of about 0.01 mm of mercury, and a high voltage of 1000 volts. So this is the condition at which gas conducts electricity. So he said, what happened during electrical breakdown of a gas? When this happened, electrical breakdown, ionization occur, then the gas suddenly becomes what? Conductive. So that is the correct option, which is option C. I hope we are together. So the last question on this session, the final question on this particular 2025 practice questions. So it's question 40, which says, which of the following statement about nuclear fusion is correct? So if you read through your nuclear physics very well, you will be able to understand the difference between fusion and what and fission. In fusion, two smaller a light nucleus come together to form what? A heavier nucleus plus what? Energy release, right? While the fission is the breaking down of a heavy nucleus into a smaller nucleus plus what? Plus energy release. So there are much differences between fusion and a fission. Is that understood? So which of the following statement about fusion, nuclear fusion is correct? So option A says it produce long-lived radioactive waste. It is established that the waste generated is very relatively small compared to the waste generated from fission. B, it is currently widely used in power plant. No, it has not been commercialized because of a certain condition that need to be met, as in the temperature at which that it required to be in operation is very, very high, in millions of what? In millions of kelvins. Are we together? And option C say it requires lower temperature than fission. No, it requires very gigantic temperature to be in operation. And according to what I understand, the temperature can only be gotten in the core center of the sun. So although there are um, things going on for it to be in commercial use, but as at now, the most efficient one is the nuclear fission for power generation. So, and option D says it produces more energy per nucleon than fission. Yes, the energy produced by fusion is very much more than fission, but that condition needed to be met, which is the temperature required, or the material that can withstand that temperature is still in developing stage. So, but it is known that the energy that we can get there will be far more than that of what? Of fission. So the correct option here is option D. It produces more energy per nucleon than fission. I hope this is understood. So we are going to stop here, which is the final session of the 2025 past question solution series. If there's anything you don't understand throughout from question 1 down to question 40, please let me know in the comment section, and also tell me which year do you prefer we should take in our next class. So thank you for your time. I hope you enjoy the class. See you in the next session of practice. God bless you.